Section 4.5, the dimension of a vector space. First, let's look at a theorem. Theorem 9 says if a vector space V has a basis beta equal to the vectors b1 through bn, then any set in V containing more than n vectors must be linearly dependent. And let's look at a proof real fast of this. First, we're going to suppose that we have a set of vectors, u1 through up, that are in V, and we're going to assume that p is greater than n. So then we know that the coordinate vectors of each of those are in Rn space. Since p is greater than n, we know that the set of the coordinate vectors are linearly dependent. And that's because there's more vectors p than there are entries n, because these vectors are in Rn space. Therefore then, the set containing those vectors u1 through up is linearly dependent. And that is from something we looked at in section 4.4. Now let's look at theorem 10. If a vector space V has a basis of n vectors, then every basis of V must consist of exactly n vectors. So we're going to look at a proof of this as well. First, let's suppose we have beta sub 1, and that's a basis for V that has exactly n vectors. And now we're going to suppose that beta sub 2 is any other basis for V. And what we're going to do is we're going to show that they both have to have exactly n vectors. So by the definition of a basis, we know that both beta sub 1 and beta sub 2 are both linearly independent sets. And then by the theorem 9 we just looked at, if beta sub 1 has more vectors than beta 2, then beta 1 is a linearly dependent set, which it can't be since it's a basis. And by theorem 9, likewise, if beta 2 has more vectors than beta 1, then beta 2 is a linearly dependent set, which it cannot be since it's also a basis of V. So therefore, beta 2 has exactly n vectors as well. Now let's look at a definition. If V is spanned by a finite set, then V is said to be finite dimensional, and the dimension of V, written as dim V, is the number of vectors in a basis for V. The dimension of the zero vector space, consisting of just the zero vector, is defined to be 0. If V is not spanned by a finite set, then V is said to be infinite dimensional. So let's look at an example. First, the standard basis for P3 is the set containing the vectors 1, t, t squared, and t cubed. And remember, P3 is the set of polynomials of highest exponent of 3. So the standard basis is these vectors here, which is 4 vectors, which means then that the dimension of P3, that vector space, is 4, since there were 4 vectors in the basis. Okay, likewise, the standard basis for P2, which is the set of polynomials with greatest exponent of 2, is the set containing the vector 1, t, and t squared. So that has 3 vectors in the basis, which means that the dimension of P2 is 3. So in general, the dimension of our polynomial spaces, P sub n, is going to be n plus 1. And the space P of all polynomials, where we're not limiting it to what the highest exponent can be, that is infinite dimensional. Let's look at another example. The standard basis for Rn is the set containing these vectors e1, through En, where E1 through En are the columns of the identity sub n. So for example, the dimension of our space R3 would have E1 through E3, which is 3 vectors in the standard basis, and so the dimension would then be 3. So in this example, we want to find a basis and the dimension of the subspace given here. So the first thing we're going to do is separate this out, grouping our A, B, C, and D terms together. So I'm going to factor out A, and I have the vector 1, 2, 0, 3, plus B times the vector 1, 2, 1, 0, plus C times the vector 2, 4, 1, 3, plus D then times the vector 0, 1, 1, 1. So I'm going to call these individual vectors V1, V2, V3, and then V4. So then we can say that our set W is equal to then the span of those 4 vectors, V1 through V4. So if we set this up as a 4x4 matrix, here with V1 through V4 as the column of our matrix, and we row reduce it, we end up with this matrix here. And we can see that V3 is a linear combination of V1 and V2, since this matrix here, if we called it, let's say U3, was made up of U1 plus U2. So let's have a look and just double check. We can see that V3 is equal to V1 plus V2. And so if we add those, we have 1 plus 1 is 2, 2 plus 2 is 4, 0 plus 1 is 1, and 3 plus 0 is 3. So that is true. So then, by the spanning set theorem, since V3 was a linear combination of V1 and V2, it's extraneous, so we can discard V3. And also notice that V4 is not a linear combination of V1 and V2. Essentially, we had pivots in the space of V1, V2, and V4. So then we see the set containing V1, V2, and V4 is a basis set for W. So then that means then that the dimension of W is equal to 3. The dimension, remember, of our space is the number of vectors in our basis set. So the dimension is 3. In this example, we're going to look at dimensions of subspaces of R3. So first, the zero-dimensional subspace contains only the 0 vector. So this is the 0 vector for R3. And this would be a zero-dimensional subspace. A one-dimensional subspace, the span of V, where V is not 0, so we have 1 vector in the span, that is in R3. And these subspaces are then lines through the origin. A two-dimensional subspace is the span of 2 vectors, u, v, where u and v are in R3 and are not multiples of each other. So then these subspaces are planes through the origin. And then a three-dimensional subspace, the span of u, v, and w, where those vectors are linearly independent vectors in R3. This subspace is R3 itself because the columns of A span R3 according to the invertible matrix theorem. Now let's look at theorem 11. We're going to let H be a subspace of a finite dimensional vector space V. Any linearly independent set in H can be expanded if necessary to a basis for H. Also, H is finite dimensional, and we have that the dimension of H is less than or equal to the dimension of our vector space V. So in this example, we're going to let H be equal to the span of these two vectors here. Then we see that H is a subspace of R3, and since H is the span of these two vectors, it's the column space of a matrix, so we know it is a subspace. And the dimension of H is less than the dimension of R3. Since the dimension of H is 2, and then the dimension of R3 is 3, and we know that 2 is less than 3. We could expand the spanning set from what we originally had with the two vectors to this second set here, where we basically add the last column of our identity in order to form a basis for R3. Now let's look at Theorem 12, the basis theorem. We're going to let V be a p-dimensional vector space where p is greater than or equal to 1. Any linearly independent set of exactly p vectors in V is automatically a basis for V. Any set of exactly p vectors that spans V is automatically a basis for V. So in this example, we want to show that this set here is a basis for P2. So we're going to call this first vector V1. This second vector here is going to be V2. And this third one we're going to call V3. And remember then that the standard basis for P2 is the set containing 1t and t squared. So our coordinate vectors, where we're going to use the standard basis, we're going to rewrite then the coordinate vector for V1 is going to be equal to 0, 1, 0. Then the coordinate vector for V2 is going to be equal to 1, negative 1, 0. The coordinate vector for V3 is going to be equal to 1, 1, negative 1. And remember, we're basically saying we're trying to rewrite these as a linear combination of the standard basis. So V1 was equal to 0 times 1 plus 1 times t plus 0 times t squared. And so then these are the coefficients, and those form our coordinate vector. And we do the same thing for V2 and V3. Notice that the coordinate vector for V2 is not a multiple of the coordinate vector for V1. And also the coordinate vector for V3 is not a linear combination of the coordinate vector for V1 and the coordinate vector for V2. Since there's no multiples, we could multiply this third entry in either one in order to add them together then to get a number, since they're both 0. So then we see that the set containing the coordinate vectors is linearly independent. And so therefore the set of my original vectors V1, V2, and V3 is linear independent also. And then since the dimension of P2 is 3, the set containing V1, V2, and V3 is then a basis for P2 according to our basis theorem. Theorem 12 from up above. Now let's look at the dimensions of the column space of A and the null space of A. Recall how we find basis sets for column spaces and null spaces. So in this example, we're going to suppose A is this 2x4 matrix, and we want to find the dimension of the column space and the dimension of the null space. So first we're going to look at the column space of A, and we're going to work first to find a basis. So I'm going to take my original matrix, and I'm going to multiply here by -2 and add, and we get this matrix here. And notice that I have a pivot here in the first and the third column, so then we know that the second and the fourth column are free. So remember then, when we're finding a basis for the column space, we're using the pivot columns. So then our basis set would be the set from our original matrix containing the first column of A and then the third column of A. And this is a basis for the column space of A. And since that's a basis, we know then that the dimension of the column space of A is then equal to 2, since there are two vectors in our basis. Now the column space was a little easier. Now we're going to look at the null space of A. Remember that we want to solve our homogeneous equation AX equals 0 by row reduction of our augmented matrix containing A and then zeros. So here's my augmented matrix, and I'm going to row reduce it, and we'll get this matrix here. So remember now with null space we're writing the general solution. So we have that x1 is equal to negative 2x2 minus 4x4. x2 is free. x3 is equal to 0, and then x4 is free. So our general solution would be x2 times negative 2, 1, 0, 0 plus x4 then times negative 4, 0, 0, 1. And so these two vectors here are going to be the basis for the null space of A. So those two vectors are in our basis set for the null space, and there are two vectors, so then the dimension of the null space of A is also equal to 2. So an important note then, the dimension of the column space of A is equal to the number of pivot columns of A. And then the dimension of the null space of A is the number of free variables of A. So if all you're being asked for is the dimension of the column space or the dimension of the null space, and you aren't actually trying to find the particular vectors that are in the basis, then you can simply row reduce your matrix A and identify your pivot columns. The number of pivots is the dimension of the column space. The number of free variables then is the dimension of the null space.